We have looked at rectilinear motion, followed by some special cases of curvilinear motion, including projectiles. All this time, we've been using Cartesian coordinates. But now we'll start to analyze more complicated examples of curvilinear motion, and alternative coordinate systems can help us with this. Before we get to those coordinate systems, though, let's cover some background information. We'll start by thinking about angular motion. We can describe an angular position with an angle theta. By convention, theta is measured from a reference line and is positive in the counterclockwise direction. Recall also that if theta is a function of time, the magnitude of the angular velocity omega is equal to theta dot, and the magnitude of the angular acceleration alpha is equal to omega dot or theta double dot. Note that even though we may be describing the motion of a particle using angular positions, velocities, and accelerations, the motion of the particle is still curvilinear. The particle itself is translating but not rotating. We will define theta, omega, and alpha more formally as vector quantities later, but for now, just be aware of these terms and what they represent. With that as background, let's look at this example. A particle P is moving along a spiral path such that r equals 0.5 theta, where theta is in radians and r is in meters. We're asked to determine the particle's acceleration vector viewed from an Earth-fixed reference frame when theta is pi over 2 radians, theta dot is 2 radians per second, and theta double dot is 4 radians per second squared. We've been working problems where the position of our particle is described by the Cartesian coordinates x and y. However, in this problem, we're given r, a distance from the origin to the particle of interest, and theta, an angular position measured from a reference line. You actually already have the tools to solve this problem, and I will work through it using what we already know. But then I'll give a simpler approach for problems like this. You will not be tested on this longer process, but I recommend that you watch it once because it incorporates a lot of fundamental aspects of kinematics that will help you going forward. So to solve this problem, first, draw a picture and add an Earth-fixed reference frame. Realize that even though we have information in terms of r and theta, we can describe the particle's position in terms of x and y. Next, realize that we need to find the acceleration of p with respect to e. Using basic kinematic equation 2, we see that we can find acceleration if we have velocity. Using basic kinematic equation 1, we see that we can find velocity if we have the position vector. So let's start by writing an expression for the position vector. This is just xex plus yey. We don't have a lot of information about x and y, but we do have information about r and theta. So let's see if we can't write x and y in terms of r and theta. You probably already know that x equals r cosine theta and y equals r sine theta, so let's plug those expressions into the equation for the position vector. And we get the position of p with respect to e equals r cosine theta ex plus r sine theta ey. Now we can differentiate to find velocity. Using the product rule and the chain rule, we get the velocity of p with respect to e equals r dot cosine theta minus r theta dot sine theta in the ex direction, and r dot sine theta plus r theta dot cosine theta in the ey direction. Don't hesitate to pause the video to make sure you understand how this derivative worked. I'm going to ask you to remember this final equation. I'm going to recreate it in a different way later. Now we're going to follow the same procedure for acceleration. I'm going to add additional colors to the terms in the velocity expression so it's easier to see what happens when we differentiate. You may need to pause the video again in order to follow every step. Here is the derivative of the velocity vector. And then just collect terms, and this is the expression for acceleration. Now that we have an expression for acceleration, we can start to plug in the additional information we have. We know that r is 0.5 theta, then r dot must be 0.5 theta dot, and r double dot is 0.5 theta double dot. We can substitute these values into the equation for acceleration and collect terms. And now we can plug in values. And I'm going to start by noting that theta is pi over 2 radians or 90 degrees. And so the sine theta is 1 and cosine theta is 0. This gives us a much shorter expression for acceleration. Now I'll evaluate the expression when theta is pi over 2 radians, theta dot is 2 radians per second, and theta double dot is 4 radians per second squared. And we find that acceleration is negative 7.14 ex minus 1.14 ey, and that's in meters per second squared. You might want to remember this last expression. You will see it again as well. Once again, I need to cover some background material before we can go any further. Recall from the first video that I said vectors that have the same magnitude and direction are equivalent. Consider vectors q and r. Let's assume that these vectors have the same magnitude or length. And let's also assume they have the same direction. Then they must be equivalent vectors. Now let's say that our vector r stretches to 1.5 times its original length. The magnitudes of q and r are no longer the same, even though their directions are. So they are not equivalent vectors. Let's reset r so it's the same length as q again. And now let's say the vector r starts to move along a curvilinear path. Even though it's moving, its orientation is not changing, and it's the same length as q. Therefore, q and r have the same magnitude and the same direction, so they must be equivalent vectors. Let's have r come to a stop, but let's have it rotate a few degrees, such that its direction is no longer the same as q. Q and r have the same magnitude, but different directions now. So here again, q and r are not equivalent vectors. What if r starts to rotate and continues to rotate? The magnitudes of q and r are still equivalent, and the directions are now the same only once per rotation, when r is aligned with q. We can say at this point that q and r are equivalent only once per rotation. Now let's think about a unit vector. We will call this one u sub r. And in order to help us understand the motion of u sub r, let's add an earth-fixed or inertial reference frame. Now we can say that with respect to reference frame E, UR starts out stationary, but then let's say that UR starts to translate along a curvilinear path. Notice that its orientation is not changing with respect to reference frame E, so it is not rotating. Now here's a question that you probably haven't encountered before. Can you take the derivative of u sub r? As it turns out, you can, but you have to take the derivative with respect to a specific reference frame. And we'll denote this reference frame using a subscript outside the parentheses. So this would be said, the derivative of UR with respect to time as seen from or as taken in the E reference frame. For example, let's see if we can figure out what the derivative is. Recall from before that as long as a vector isn't stretching or shrinking, then its magnitude is constant. This is a unit vector, so its magnitude is always 1. It is constant. Recall also that if a vector isn't rotating, then its direction is constant. If UR has a constant magnitude and a constant direction, and the derivative of a constant with respect to time is 0, then the derivative of UR as seen from E must be 0, or more specifically, the 0 vector. Now what if UR was rotating? What would the time derivative as taken in the E reference frame be? In this case, the magnitude is a constant 1, but the direction is changing. This suggests that UR is not constant, which means that its time derivative is not 0. I will do this derivative in a few minutes, but for now, just remember that the time derivative of a translating unit vector is 0, but the time derivative of a rotating unit vector is not 0. So let's move on and let's think about polar coordinates. Polar coordinates will typically work like this. Let's say we have a particle P in the Cartesian reference frame such that the position of P with respect to E is xex plus yey. We can also add a polar coordinate system such that the radial unit vector, u sub r, is fixed in the particle and directed away from the reference point E. We can also add the transverse unit vector u sub theta such that it is fixed in P and directed toward the direction of increasing theta. The coordinate system moves with the particle such that at any time t, the position of P with respect to E equals r u r, where r is the radial coordinate. Polar coordinates are a bit tricky to visualize, so here's an animation. As the particle moves, the inertial reference frame E remains fixed, but the unit vectors of the polar coordinate system rotate with the particle. Although it is difficult to animate, try to imagine that the particle could also be moving closer to point E and then farther away from it. As it does, distance r is also contracting and stretching over time with the particle, such that the position of P with respect to E is always r u r, but r is not necessarily constant. Try to imagine yourself standing at point E and rotating such that point P is always in front of you. From your perspective, you would never describe P as moving from side to side. That is how you can think of the position vector. It's always pointed in the UR direction, even though UR is rotating with respect to reference frame E. Recall how I said that any two vectors that have the same magnitude and direction are equivalent. If that is the case, then we can place the U unit vectors in the particle as shown on the left, or at point E as shown on the right. Doing the latter makes it easier to see that you can convert rather easily between polar coordinates and fixed Cartesian unit vectors using the expression shown. These will work as long as UR is aligned with EX and U theta is aligned with EY when theta is 0, and these expressions will work for any value of theta. Don't hesitate to pause the video and make sure you see how to convert from polar coordinates to Earth-fixed Cartesian coordinates. I will do an example shortly, but you'll need to know how to do this on the homework. Up until now, we've been working exclusively with Cartesian coordinates. We can always work problems in an Earth-fixed Cartesian reference frame. However, sometimes it is convenient to add a second reference frame that uses a different coordinate system. Now we're going to start working with polar coordinates. We will refer to the coordinates of the system as follows. R is the radial coordinate. It is the distance from a base point to the object of interest. Theta is the transverse coordinate. It is the magnitude of the rotation from the reference line to the radial unit vector. Z is the height coordinate. If we were working in 3 dimensions, it would express the distance from the UR U theta plane to the object of interest. The unit vectors of the system include UR, the radial unit vector, U theta, the transverse unit vector, and UZ, the height vector. This is a right-handed coordinate system such that UR cross U theta equals UZ. Typically, we set up the unit vectors such that UR equals EX and U theta equals EY when theta is 0. And in this class, we'll almost always set up the system so that UZ is equal to EZ. But this reference frame will rotate with respect to the inertial E reference frame. At this point, I'm going to derive a set of equations that we can use with polar coordinates. You will not be tested on this derivation, but please watch it at least once because it contains a number of concepts that will become more important later in the course. There will also be a summary and example later in the video. So we know that the position of a particle P with respect to some point E can be written as RUR in polar coordinates. But since we will frequently be interested in the velocity and acceleration of the particle, we know we will need to take its time derivatives. It turns out that the reference frame in which you take the time derivative is important. When we were only working with a single reference frame, it wasn't an issue. But now that we'll be working with more than one reference frame, we'll need to be careful. At this point, I also need to give you a bit more information about the subscript notation we've been using. When we refer to the position vector, the second letter in the subscript refers to the base point of the vector, which often corresponds to the origin of the reference frame we're using. This is not new. However, for velocity and acceleration, the second letter in the subscript actually refers to the reference frame in which the derivative is taken. So let me show you how this works. Let's say we want to find the velocity of particle p as seen from the E reference frame. We need to take the derivative of the position vector in reference frame E, and we'll do that by adding another subscript outside the derivative. And it must match the second letter in the velocity subscript. So let's continue and take the derivative of the position of p with respect to E. If we're working with polar coordinates, then the position vector is given by RUR. But since the unit vector UR is rotating with respect to the E reference frame and its direction is changing, then the time derivative of UR in the E reference frame is not 0. If this doesn't quite make sense, then take a look at UR and U theta as they relate to reference frame E. As long as they're only translating with respect to E, then we don't need to worry too much because they're still equivalent vectors. Their magnitudes and directions remain constant. So they are constant vectors and their time derivative taken in the E reference frame is 0. However, if they start to rotate, then their directions are changing. They're no longer constant vectors and their time derivative in the E reference frame is not 0. The takeaway here is that we need to be careful when taking a derivative when one reference frame is rotating with respect to another. But we'll come across this from time to time, so we need to account for the rotation when we take the derivative. How do we do that? We use the product rule. So using the product rule, if we wanted to take the derivative of RUR in the E reference frame, we would get R dot UR plus R times the derivative of UR with respect to time in the E reference frame. The time derivative of UR is tricky, but it would be easier if we could write UR in terms of the E unit vectors. And in fact, we do know how to do this. Sometimes the conversions are easier to see if you draw the diagram of the unit vectors. Don't be afraid to do this. So UR is just cosine theta EX plus sine theta EY. Substituting the expression for UR into the expression for velocity gives this. Now notice that the E unit vectors are fixed or constant with respect to the E reference frame. So their time derivatives with respect to E are 0. So we don't need the product rule again. And the velocity of P with respect to E becomes this. Now we can take the derivative applying the chain rule. I'm going to rearrange a bit strategically. So now we should be able to see that the expression in parentheses is U theta. Substituting U theta back into the expression, we find that in terms of polar coordinates, the velocity of P with respect to E is R dot UR plus R theta dot U theta. Note that this is the velocity of P as viewed from reference frame E. Even though the unit vectors are in polar coordinates, this is still the velocity of P as viewed from E. If you need to convert it back to the E unit vectors, you can do so using the conversion equations. If you do, you'll get this expression, and this should be the same equation I asked you to remember from before. What I hope you take away from this is that these two expressions are equivalent, but it's often more convenient to work in terms of polar coordinates, which are rotating with the particle of interest. If you follow the same procedure for acceleration, you'll end up with this expression, and it converts back to the same equation we obtained when we used only the Cartesian coordinate system. Going forward, we can use these expressions to help us find the velocity and acceleration of a particle using polar coordinates. Be aware that the particle is not rotating, but the polar coordinate system is rotating with respect to the Earth fixed reference frame in order to track the curvilinear motion of the particle. Remember that you can always work problems using an inertial reference frame only, but because that can lead to cumbersome derivatives of trig functions, it is often more convenient to use a second reference frame as well. Also note that these expressions came directly from the basic kinematic equations. So let's revisit the problem from before, where our particle was moving in a spiral. We're asked to find acceleration, so let's add polar coordinates and use the corresponding equation for acceleration. We note that we're going to need not only r, but also r dot, r double dot, theta dot, and theta double dot. We were given values for theta dot and theta double dot in the problem statement. If r is zero point 0.5 theta, then r dot must be zero point 0.5 theta dot and r double dot is zero point 0.5 theta double dot. Now we can plug these expressions into the equation for acceleration, add values, evaluate, and collect terms. You can leave your final answer in terms of the polar unit vectors, but if you want to convert to Cartesian unit vectors, you just use the same conversions as before. I will plug in the expressions for UR and U theta and evaluate, noting that sine theta is 1 and cosine theta is 0. Rearrange and we get the same answer as before, but it took much less time. So going forward, you can use the polar coordinates along with the expressions for velocity and acceleration that go with them.